Okay, in this video we're going to talk about the acetoacetic ester synthesis. This is a very interesting reaction because in this set of reactions here, we are going to add or make a new carbon-carbon bond and then also break a carbon-carbon bond. So this reaction starts with the acetoacetic ester, and that is this compound here. So obviously this is our ethyl ester, and the name of this compound is the acetoacetic ester, and that is the starting material we use for this synthesis. If we take a look at the reagents, here this is 3 steps, and we can see the number of steps can actually vary between 3 and 5, or even 6, depending on how many R groups we have. In this example, we're going to add on just 1 R group, so it's only a 3-step process. But we can actually repeat steps 1 and 2 before we do step 3 to add on 2 R groups, and we'll see that in our next example. The other thing I want to point out is step 3 is treating the compound with acid and heat. There's actually 2 ways to do this. This is the simpler method. It takes 1 less step, but occasionally you might see this written out differently. So instead of just step 3, you could have step 3 where you treat your compound with sodium hydroxide first, and then step 4 the compound is treated with acid and heat. And basically what step 3 is going to do is do 2 reactions. You're going to hydrolyze the ester and then do a decarboxylation reaction, which we'll talk about in a little bit. And you can do that hydrolysis reaction with just acid, or you can use saponification, which is sodium hydroxide followed by H+ or heat. So there's really 2 ways to do this 3rd step. Just acid and heat, that's easier, or a 2-step process, 3 and 4, sodium hydroxide followed by H+ and heat. And we'll go through this process. So overall, I just want to point out a few things. Let's label the carbons that we have on our acetoacetic ester. So carbon 1, 2, 3, and then carbon 4, I'm going to draw in red. If you look at our product, where our starting material, the acetoacetic ester, has 4 carbons connected, our final product only has 3. So we have carbon 1, 2, carbon 3. So only these 3 carbons are found in our product. The other thing we have is, so what that means is this 4th carbon, this C double bond O to the OT, is gone. And that's lost as carbon dioxide in the reaction. And as we go through the mechanism, we'll see how that happens. The other thing to note is we're making a new carbon-carbon bond with our R group, and that new bond happens from carbon 3 to carbon to our R group here. So overall, we have 4 continuous carbons, only 3 are in the product, step 1, 2, and 3, 1, 2, and 3. The carbonyl in the ester is gone, and that is really replaced with whatever our R group is. The other thing I want to point out is here we started with the ethyl ester. The first reagent we add is sodium ethoxide, and the key here is that the base that we use has to match the ester. So if this is an ethyl ester, as shown, we need to use sodium ethoxide. If this was OMe, a methyl ester, then we would have to use NaOMe. And the reason for that is, if we treated the ethyl ester with NaOMe, we'd have a competing reaction of trans-esterification, meaning that the OMe would attack the carbon of the carbonyl and replace the OET group. We do not want that to happen. Product or reagent 1, NaOET, we do not want to react as a nucleophile, we want it to act as a base. So this compound here is a base. And the best base for us to use is the base NaOET because that matches the OET on that ester. So let's start going through the mechanism to see what happens here. obviously in step 1 we add sodium ethoxide. So that is ETO minus. So let's just draw that in. And again, this base matches our ester, so it's only going to react, in fact, as a base and not as a nucleophile. So what I'm going to do now is draw in the 2 hydrogens that are most important. And they're most important because these 2 hydrogens are most acidic. These hydrogens are on the alpha carbon, and it's the alpha carbon to both carbonyls. It is in between both of them. Carbon 1 is also an alpha carbon, but it's only alpha to carbon 2, that carbonyl. So if we think about what happens with the base is obviously going to deprotonate one of these hydrogens, putting a lone pair on the alpha carbon. So let's draw out the product we get. And from looking at the product, we will be able to easily identify why we deprotonate this center hydrogen. So we still have our OET. And instead of having 2 hydrogens, now we have 1. And we also have a lone pair here and a negative charge on that alpha carbon. One thing to remember, of course, is that we can draw resonance structures, and what we've just formed is called an enolate. So let's write that out. And we know that enolates are very good nucleophiles, and that we can also draw a couple of resonance structures with our enolate. So let's draw in our resonance structures. Let me draw the arrows first. So this lone pair on the alpha carbon can form a carbon-carbon double bond, pushing that double bond onto the O. And the consequence of that is we now have a double bond here, a single bond to the O. The O had 2 lone pairs, now it has 3 and a negative charge, and the rest of the molecule looks exactly the same. So that's one resonance structure we can draw, and that's where the electrons go to the carbonyl on the left. Well, of course, because it's in the middle, it can actually form a resonance structure by moving up to the carbonyl on the right. So let's draw that resonance structure here. So again, we now have a carbon-carbon double bond, single bond to our O. That has a negative, and we still have our OET group. Okay, so these are all resonance structures of our enolate, and what we really need to remember is that our enolate is in fact a very good nucleophile. So I like to use this resonance structure to show the next step, but you could do it from either of these. You just need to add an extra arrow. So our enolate is a good nucleophile, and if you look what we add in step 2, we've added an electrophile. So let's draw the mechanism, and basically what we're doing is essentially a substitution reaction. This lone pair will attack the carbon connected to the halogen and kick off that halogen. So we simply do an attack, and that will generate this intermediate here. So we have our C double bond O, our other carbonyl, and this is our ester. Again, we have 1 hydrogen here, and now we have our new bond to whatever our R group is. Okay, so the first step, our base deprotonates to form our enolate. Our enolate is a good nucleophile. It attacks to do an SN2 reaction, kicking out the Br to form this intermediate here. So this is what we have after step 2. So I'm not going to show the mechanism yet for step 3, But essentially what we're doing here is a hydrolysis. So I'm just going to draw a couple arrows indicating that this is a couple of steps. And remember, what's going to happen is we have our C double bond O, and instead of our OET, that is going to be hydrolyzed to an OH, to a carboxylic acid. So step 3, the acid will do the hydrolysis. So we'll go from an ester to a carboxylic acid. And that reaction can happen two ways. It can happen under acidic conditions. This is our leaving group. Water is our nucleophile, catalyzed by acid. The mechanism of this process is pretty long. Protonate attack, deprotonate, protonate eliminate, deprotonate. And you can get your hydrolysis that way. Or you can do it by saponification. Saponification is NaOH followed by H+. And that's why there's two methods to do this. Either acid-catalyzed hydrolysis or base-catalyzed hydrolysis, which we call saponification. Regardless of your method, the ester becomes the carboxylic acid. Okay? Our ester is our carboxylic acid. Now, in our last step, this step still happens in either the third step, H+ in heat, here at 3, or there as 4, H+ in heat. What we see happens is our carboxylic acid that I originally had in red is gone. So this fourth step here after your hydrolysis is our decarboxylation reaction. Decarboxylation. Okay? So the decarboxylation reaction is what is responsible for having this C double bond O OH be removed via a loss of carbon dioxide, and that now is a hydrogen here. So that group has been replaced and is with a hydrogen. So if you look at carbon 3 now has two hydrogens attached. So I want to go into a little more detail about this decarboxylation reaction, and I'm going to just show that on our next slide. So here's our decarboxylation reaction. This is the same exact product that we had before. We have our R group in blue, and now our carboxylic acid, so this has already been hydrolyzed. And I'm going to show you the mechanism of how the decarboxylation reaction happens. Okay? To do this, what we actually need to do is redraw our product in a better configuration. So I'm going to just rearrange how my carboxylic acid is drawn. So I'm going to have my C here. I'm just going to move the OH up and the C double bond O kind of in the plane. So all I've done is rearrange this carboxylic acid. I have this alpha carbon to the carbonyl, alpha carbon to the carbonyl. And the mechanism of this process happens under heat. The double bond on the O forms a new bond to the OH. The HO bond forms a new carbon-oxygen double bond, and this carbon-carbon bond forms a carbon double bond on the species. So if you look what we've drawn, I now have a single bond to OH. I have a carbon-carbon double bond here. And then in red, I have my C double bond O and C double bond O. And I've tried to draw these in the same configuration that we saw here. So essentially the key here is I've broken this carbon-carbon bond here. And this is an electrocyclic process. There's 6 electrons moving in a cycle, kind of like the Diels-Alder reaction, but the result is it breaks this carbon-carbon bond. And once you form carbon dioxide, this carbon dioxide is going to be released as a gas. And I just noticed I forgot my R group, so let's include my R group here. And then if you look at this compound, it should be easy for you to identify that this compound is simply an enol. And what we can remember is that enols easily undergo tautomerization to the keto form. So here we have the keto form, and the keto form is more stable. So all we've really done here is tautomerization. So we've done tautomerization to go from our enol form to our keto form. So this is the last step in the mechanism, the decarboxylation reaction. We redraw the carboxylic acid. We have the 6-electron process which forms the enol, and the enol can undergo tautomerization to form our ketone. And that is in fact our final product. Okay, so let's look at one more example here. So here is a reaction, and I want to go through exactly what's happening. Again, what I'm going to do is number my carbons. Carbon 1, 2, 3, 4. We remember in the acetoacetic ester reaction, 1, 2, 3 results from our starting material. In our first step, we have sodium ethoxide that will deprotonate this product. So here I'm not going to draw the arrows for that. I'm just going to draw the intermediate. So now instead of 2 H's, we have 1 H. We have a lone pair and a negative charge. Remember that this is now our enolate. I can draw 2 resonance structures for this compound, and it is a very good nucleophile. So what happens is this is a good nucleophile. It does an SN2 reaction in the second step. So let's redraw those arrows so it's a little clearer. We backside attack the carbon of the carbonyl, kick out the Br. So I'm going to draw this new group, the cyclohexyl group, in blue. We've added that to the alpha carbon. This is still connected to our ethyl ester, OET. And now you'll notice we repeat this process again. So in step 3, I add sodium ethoxide, and then again I add an electrophile. So I can actually add on 2 R groups. The same exact things happens. This hydrogen will get deprotonated to form an enolate. The enolate will attack and do an SN2. So let's just draw this intermediate that we form after. So let's take that same material, and I'm just going to erase. I no longer have that hydrogen bond. I now have an ethyl. So I have 1, 2 carbons from our ethyl. So this is the product we have after step 2. This is the product we have after step 4. One little note I want to make is that in step 3 we use sodium ethoxide again. Another base you can use, which is pretty common, is potassium T-butoxide. So potassium K-O- next to a tert butyl group. So we can have K plus O- next to a tert butyl group. So this is a very common base we can use for this reaction. And now we need to complete this reaction. Here you'll notice we have step 5, H plus and heat. So what does that reaction do? Remember that the acid is going to hydrolyze our ester. So let's draw that in. And instead of the OET, we're now going to have an OH. And if you remember, the last step that happens here is our decarboxylation step, where we lose that carbon. There's our decarboxylation step. So this whole carboxylic acid and the carbon is now gone. So if we compare these products, carbon 3 has our ethylene green, and it also has a bond to our cyclohexyl ring here, and that is the final product. So in summary, we treat with a base to form a good enolate. Enolate attacks and does an SN2 to make our new carbon-carbon bond. We repeat this process again in steps 3 and 4. I use sodium ethoxide or potassium T-butoxide is fine, and that H is deprotonated and replaced with an ethyl group via an SN2 reaction. Step 5, acid hydrolyzes this ester to the carboxylic acid, and then we do the decarboxylation reaction where this carboxylic acid has now gone. We've lost CO2. Okay, so that other carbon that we've lost is carbon dioxide, leaving with this compound here. 1, 2, 3 carbons from our starting material, 1, 2, 3. 6-membered ring from our first electrophile, 6-membered ring. Ethyl group from our second electrophile, ethyl group here, and that is our final product. And a full tutorial on how to do the acetoacetic ester synthesis. Okay, the last thing, the problem I want you to work on, is I want you to synthesize this compound using the acetoacetic ester synthesis. Okay? So obviously our starting material is our acetoacetic ester. It's up to you which one you want to use, whether you use the ethyl ester or the methyl ester. It doesn't really matter. So essentially what I want you to do is complete this synthesis. Start with this starting material and make this compound. Remember, 1, 2, 3 carbons come from here. 1, 2, 3 carbons are represented there. So that should it should be easy for you to identify what your electrophile is in this case.